not convergent. So not many people dare to play with extrema. And we have already break the new grounds if we want to extrema. But if you go beyond that, you look for x double prime, x triple prime, so on and so forth. Is that meaningful? Perhaps. But you see, in fact, for any function, we can expand it out in Taylor series. And that means that if you know the function, you know the nth derivative of that function, then you can evaluate the function for a convergent radius of A anywhere. You can evaluate the function. So there must be hidden values for a lot of functions. So where should we start? Where should we stop? So what we did is that we generally stop at the extrema. We don't usually go beyond extrema. In case, however, if you really want to know whether they are hidden scale or not, you can go to curvature. The curvature by definition is x double prime 1 plus x prime squared to raised to the 3/2 power. That's the definition of curvature. But that is only curvature. The curvature is not what that becomes our data. So the hidden scale, therefore, beg a question. The question is that, is this a scale? Do we have another wave that's hidden there? Okay. But there's no end to this because, of course, we have x equal to 0, we have x prime equal to 0, and if we're looking for this, then we have to look for the curvature extrema, see whether there's any curvature change. And the curvature change is actually more than the inflection point. The inflection point x double prime equal to 0. If we look for curvature, curvature definition is already x double prime. Okay, so to look for this hidden scale, we have right now the present shifting is already one step further than zero crossing. In the past, I have mentioned it to this class before. In the past, people studied noise, especially S.O. Rice. In the 40s, he studied the noise in the telephone. And by studying noise, what he finds is that if you look for zero crossing, that's very stable. Zero crossing is the second moments of the spectrum divided by the zeroth moments, square root, the expected number of zero crossings. But if you try to involve extrema, that's x prime equal to 0, then it will call for the fourth moment of the spectrum. Fourth moment means if spectrum frequency is the frequency spectrum times the frequency to the fourth power, and if that is that's proportional to the number of extrema. For most of the spectrum, by the time you try to calculate expected number for extrema, it's already blow up. It's not convergent. So not many people dare to play with extrema. And we have already break the new grounds if we want to extrema. But if you go beyond that, you look for x double prime, x triple prime, so on and so forth. Is that meaningful? Perhaps. But you see, in fact, for any function, if we come to here, this part concave down, this part concave up. Somewhere around here, its curvature equal to 0. Okay, so concave up and concave down, there's an extrema here, it's an extrema over there. So you find two more extremas. For curvature shifting, you actually look for the extrema of the curvature and make that a critical point, that a critical point. So when you plot the maximum, you plot this point, connect to that point, connect to this point. When you plot minimum, you connect this point and that point and this point. So once you involve curvature shifting, you actually are calculating the third derivative of the curve already. Because you not only calculate radius curvature, you are actually calculating the extremas of the curvatures. So that is a very, very detailed, very, very fine scales. Because of that, we usually do not go to curvature. But in one of the software that we prepared, there's an option that you can actually go to curvature derivative, curvature shifting. Now, the justification for us not going beyond extrema is very simple. My background is mechanics, so I start from a mechanical point of view. The mechanical point of view is that if x is position, then the second derivative is acceleration. Then when you go beyond acceleration, we don't have any physical law to govern it. So even if we find it, we don't know what it means. And so that's why we just stop. Most of the time we start at the extrema. And if we decide to go to curvature, then we have to be prepared for the consequences. The consequences here is sometimes pretty severe. For example, later we'll get into Duffing pendula. At the beginning I talked about Duffing pendula. The peak is peak is sharp and trough is sharp. And in between the sharp peak and trough, there's a shift, and there's a inflection point. And with the inflection point, there are always two curvature extremas. Okay, inflection point to curvature is zero crossing. Yeah, cross zero. So in that case, the Duffing pendula would produce more than one component. When we produce one component, it's very easy for us to interpret it. So that's easy because there are two scales. The frequency switch back and forth. But when you use curvature shifting, you will have more than one component. You get two components. That means in that pendula, there are two scales. It still can be explained, but the explain is less direct, less fitting to our physical perspective. So curvature shifting is used sparsely. I don't use it very often. It is useful in the first couple of components to get rid of noise. If your data is very noisy, sometimes I use this. But you see, any time you use derivative always introduce noise. And if you use derivative to get rid of the noise, and the result you got is usually pretty smooth. Yeah. So curvature, usually people don't do this, and in the program that we provided on the website, there's no curvature extrema. This is very important, the intermittency. We all have experience of intermittency. For example, at the beginning of the class, we have this terrible high-pitch, high-frequency noise. I believe that's intermittency. It does not occur all the time and it suddenly disappeared. And if ever you drive, you'll find sometimes your car hesitates and doesn't start. And you try it again, you take to the mechanics crank up the car, it's perfect. This is what happened. It's intermittent. Intermittency means that the system is not stable and they only occur occasionally, not always. But this occasional occurrence of this gives us a lot of problem because that generate some signal which is totally different from the system. In other words, in a very short period, the system suddenly change the state. Okay, and a moment later, it switch back to another state. Now, if we have any method, we try to decompose a signal into different scales to represent different states. And if the two states start to mix, then we will have difficulty interpreting it. So in the decomposition that I propose, there's no guarantee that it will not mix the different states together. So in order to avoid mode mixing, we have to institute some special criteria. Okay? This criteria is to separate the oscillation of different time scale to different IMF components. This criteria is selected based on the scale, so that different length scale can be sorted out differently. And later we have improved upon this, but then there's no free lunch. Anything that you do, you have price to pay. Okay, so I would first introduce this, the earliest part of its, what do we call the intermittency criteria. And to give you an example of this, is that here I have a sine wave. And on the sine wave, I put a few of the sine wave, I put some high frequency signal there. So for this frequency, we can treat this as intermittency. It does not occur all the time, but it occurs sometimes. And this does not have to be right here, the example that I put it right here. Now, if we use straightforward shifting, what do? We will extend the maximum here. The next maximum, however, the next maximum is here. Then, because there are many oscillations, then I will follow all the maximum from here, then jump over here, and then jump over here, then follow this. Then the minimum is from here to here. Instead of come to this point, then I'll have to go up to this minimum and go through here and then come back down, right? So the result is that the first trial, I'll have all the maximum or the minimum, maximum, minimum. I get all these extremas for the small waves. But where's the large wave? The large wave gets shifted down. So by shifting down this large wave, so finally I will have this small wave and some large wave and large wave to other places and so on and so forth. And you ask me, says, what is the system? Then I will give you this answer. And that answer is not very clear physically. At the beginning, I argued the following way. I said, well, it doesn't matter. Let's say each component does not represent total physical picture. But if you start to compute the frequency and project it back to the frequency, time frequency space, then it will find its own proper place. Yeah. It's true to a certain degree, but it's not totally true. And what this system actually is the data is very simple. It's a sine wave, then I put some short frequency stuff there. If I can get this result, it will be perfect. See, here, this large scale is always here, and small scale is always there. And the small scale resides with small scale, and in between the small scale components, there are quiescent places. There's nothing happened. The intermittency did not happen. How do we get this? I get this by subjectively interject a condition. The condition is that I will first guess. I will say, okay, I perhaps will go through this once, and I find that this scale is small, and I've looked up the small scale. Then I will come back. I say, all right, first I will ask the shifting to look for the extrema distance. The extrema distance, if it's smaller than 8 points, I will recognize that as a wave. If it's larger than 8 points, then I will reject it. I will not take that. I will just use the data as the original data. So as a result, I was able to take all these small wave out. The large wave, if the extrema is larger than 8 points, I ignore it. I instruct the algorithm will not recognize that point as extrema. Okay, so I only recognize the extrema if the extrema to the next extrema is less than the criteria that I put it in. So as a result, I get all this small wave out and get the large wave out. Now, let's then test my original concept. Is all right. Even if I still have this large wave, one is the envelope mean. The third one is the difference. Now this one means that you can choose any small epsilon you want, as small as you want. Then I'll always have an n step. I can try 1 time, try 2 times, try 100 times, 1,000 times. If you choose this epsilon too small, so small, then I will go very, very big n. But that n is not infinite. Okay, the finite number n, such that this mn is less than epsilon everywhere. Yeah. Now, that's a mathematical statement. The second, if we use this stoppage criteria, then we have another mathematical statement. That is given epsilon there x to the n, so that the difference between the nth and n minus 1 trial should be less than epsilon everywhere. Can we do that? I do not have a proof. And this is something that I put up to the mathematicians as a challenge. Yeah. My proof is very simple. My proof is empirical. I prove it case by case. Since the development of the method, I've used it, and many other people use it. And how many people use it? If you go to Google, there are about 2,000 people. Other people use this method and wrote papers or reports or give talks or whatever. Okay, and everyone find that it converges. But that still does not mean it is really converges. You have to have a mathematical proof that if you follow through what I say, it will really stop at the finite n. And unfortunately, I don't have that proof. Yeah, at the beginning of the course, I say that I've looked high and low everywhere, looking for people to try to help me. I put this mathematical problem squarely in the lab of the mathematician at Princeton University and Caltech. I said, well, try to prove this. We did struggle once about 10 years ago at Caltech. We did not get very far because they have problem dealing with this envelope is defined by spline. Yeah. And spline is very difficult for them to handle. Not only that, the spline is connecting of the extrema. Extrema is a special subset of the data. But there's another convergence. The other convergence is that even if each component can stop at the nth step, it stopped. Now, is there a guarantee that I give you data, you only have a finite number of components? Yeah. In fact, I've tried one method and it does not converge. It generates infinite many components. Each component converge, it stopped, but the components generate another component that keep on going. And that was when I used midpoint as the spline. Instead of using 2 splines, I used maximum minimum and connect the midpoint. And turns out that may not converge. And may not converge is you have one component, you have another component, you have another component. The scale is about the same. But each one in the finite step, it's stabilized. Yeah. So this convergence problem has 2. We have finite number of components. That's another converging problem. You cannot have infinite many. You have to go to infinite, and nobody can try infinite many times. Therefore, that is it's not converging. Now, complete proof of the convergence underway. Yeah. So empirically, if we can prove the convergence with very simplified condition, that condition is for linear connection, but that's not what we work on. So it really doesn't count. It has lots of special conditions. We can perhaps prove some convergence. So empirically, however, we found all cases converging finite step. And the finite component n is always less than log 2 base n. Yeah. So the component is finite. The EMD, as we proposed, is a dialectic filter. It will keep on doing that, and each component turns out the scale is, for example, n. The next component scale is half n and quarter n and 1/8 n. Each time it reduce to half. Yeah, that unfortunately is only empirical. No one has proved it analytically, and that in the empirical proof has been done at different locations. We have done it, and French people at École Normale Supérieure has proved it. Yeah, but all the proof is numerical. We all prove it based on white noise. We don't prove it based on any other special signals. So the necessary condition for the convergence is for the for the mean line to be less than the should have less extrema than the original. So if the component that you got has the same number of extrema as your number, that means you're not converging, because you still have the same number of maximum minimum, so the data still has the same scale as the previous, when you started. So a necessary condition is that you have to prove that my components are eliminated one extrema, at least one. Yeah. If you can eliminate one by one, and if you can prove that your method can eliminate one by one, then you'll be able to eventually get rid of all the extrema to get a straight line. Yeah. So that's necessary. Yeah. If we use the middle point and a single spline, this may not be true. Yeah. This is what I just alluded to, that the convergence, you can have components, but components does not satisfy this condition. Yeah. We have at the time that we tried this, we got the 27,000 points components, but still not stopping. So we finally stopped the procedure, and we found that, gee, we have so many components. We look at each component. The components look almost the same, have the same length scales. Yeah. So the convergence problem is by no means easy to prove, but every time we use the procedure, use the algorithm, it always gives us a finite number of components. This is a problem. This is a problem that is not proved rigorously mathematically. Yeah, but empirically, it seems to be true. The completeness means that if I have the simple certain components, if I add the components, can I get back to my original data? The answer is yes. This is given because our expansion dictates this. We always get back to the original data, even if the component does not make sense. Like, for example, the poor intermittency problem, it does not give you physical correct meaning. It's still right. Even if your end effect is terrible, it will still be right. Yeah. Every time you use this method, the method dictates that the summation of this has to be equal to the original data. So that's no problem. Orthogonality. Orthogonality means that if I have two vectors, x and y, then I have an inner product x times x1 times y1, x2 and y2 and so on. So the summation has to be 0. Yeah. Orthogonality is very simple concept, but it's very important. Why it's so important? Because if we expand x equal to cjt, and if we look for x squared should equal to cjt squared plus I does not equal to j. Okay? So all the cross product are there. Component number 1 times component number 2. Component number 2 times component number 1. And if it's a commute, so that's twice this. But since I write this way, then I don't have to write twice. Okay. I does not equal to j, all combined together. Why the orthogonality then require this term to be identically 0? Yeah. Why is that? See, if this is not 0, the problem is that it can be either positive or negative. And if it can be positive or negative, then the probability that it's negative is very high. And the probability of this as being very, very large is also pretty high. Yeah. And if it's high, then if this is not 0, then there is possibility that the x squared becomes negative. And that's very embarrassing. That means your x becomes imaginary, yeah, number. No real number square should be 0, should be negative. Yeah. If, however, if this is grossly not orthogonal, then you have a chance have a negative energy. And you have negative energy means that x squared is negative. And because of this, we always ask this to be 0. We would like to have it to be 0. And mathematical expansion always have that to be 0. Why is that so? See, orthogonality is a requirement for linear decomposition. If the decomposition is linear, orthogonality is always true. Yeah. And that decomposition, it's true if it's linear. But if it's nonlinear, it may not be true, strictly speaking. But still, it should not be grossly untrue. Why I said it may not be true? For nonlinear decomposition, as in EMD, the orthogonality should not be a requirement. For nonlinear wave, you may still have the two components may not be exactly orthogonal. For example, if I have a water wave, the water wave is very sharp crested. Right? For the sharp crested, I have to have harmonics, all harmonics. Therefore, if I have a wave of frequency 1 hertz, I have another wave of frequency 2 hertz. But each wave has all its harmonics because of the sharp crest. So the 1 hertz wave will have 1 hertz, 2 hertz, 3 hertz, 4 with so on and so forth. 2 hertz wave will have 2, 4, 6, 8, 9. So the two waves will share certain harmonics together. So when you make an inner product, all the harmonics go with it. And then it will not be exactly orthogonal. So when I made this decomposition, I did not require orthogonality. But fortunately and fortuitously, that the EMD is always and almost always orthogonal. Why? Because the EMD is basically a Reynolds type of decomposition. What do you mean by Reynolds type? Reynolds type is when we study turbulence. People study turbulence. The turbulence, of course, everybody knows turbulence velocity fluctuates up and down all over the place. Yeah. How do you study that? You say I will decompose my velocity in two components. The first component is constant, mean plus a fluctuation. Yeah, mean plus a fluctuation. Then by definition, the mean is a constant. But this constant, however, is overall constant. That overall constant is constant. So overall constant, multiply this fluctuation. Then you take average. Because this is a constant. Of course, it can take out of the average process. So your average of that is always 0. So the inner product of mean and the fluctuation is always 0. Now in our case, this EMD is not exact Reynolds, but the Reynolds type. Because I always take the components as a fluctuation from the mean. And the mean is always the next one. This mean is not the overall mean, but it's local mean. And the local mean defined by the upper and lower envelopes. Yeah. So this orthogonality is always approximately satisfied to the degree of nonlinearity. I have taken a pen in state that the EMD satisfy orthogonality to the degree of nonlinearity. Unfortunately, there are people, seems to be pretty smart people, but unfortunately they don't understand what I'm talking about. They start to attack EMD, say that the EMD is not orthogonal. And there's two possibilities. One is that they implement the EMD so poorly that you can't get components that is not orthogonal. When I do problem, if I get it get the components, I always check orthogonality. And if they are not orthogonal, I will reject it. I will reject this decomposition. My criteria is kind of loose. If the orthogonality, degree of orthogonality later will define, is higher than certain certain amount, the amount is 10%, then I will reject the result. I will not use the result. Yeah. So the orthogonality is always approximately satisfied to the degree of nonlinearity. If you have a highly nonlinear problem, grossly deformed wave, then the orthogonality still should be satisfied roughly. That orthogonality is to the degree that given by the nonlinearity. However, there's another problem. The other problem is that if the data is very short, if the data is extremely short, and not by the time that there are only few waves involved. Yeah, in this particular case, you don't have to choose very short data. For example, you shift to the last few components. Each component has only the 2 or 3 waves. Then in that case only, the orthogonality may not be very well satisfied, because even sine A times sine B average, when A does not equal to B, sine AT times BT average may not be 0 when A does not equal to B, if you only have a few waves. But the sine wave, the Fourier orthogonality, is dictated or based on infinitely long. Now, when it's infinitely long, if A does not equal to B, it definitely is 0. Yeah. So if you have finite data length, or you only have a few waves, then this condition may not be totally satisfied. Yeah. But for me, I always check the orthogonality. The orthogonality index is defined like this: Ci times Cj. Yeah. All I does not equal to j everywhere. And then I use the Ci, the total energy, and Cj total energy to normalize it, and then divide by T, because I add all the data length. That is the orthogonality of Ij. Alternatively, I can have this is Ij between I and j, I component and j component. And here this is that the Ij of all the off diagonal. This is the total orthogonality total. Every number that is not I does not equal to j, I will list it. I'll compute it, and compute it normalized by twice of the of the energy of the total signal. So this is component between the components. This is the total orthogonality index. And taking this data, for example, if I use intermittency, and I'll have very nice components separate, and if you compute the orthogonality index, I'll give you the order of magnitude. The orthogonality index between the first component to the second component is 0.0003. Between the second and third is 0.001. And third to the fourth to the fifth, and so on and so forth. You check this. This is no more higher than 4%. Yeah. And this is a very short data, especially when you come down to these components, the last few components. The last few components only have a few waves. Yeah. These components is only, say, 1, maybe 2. Yeah. And this has, say, 1, 2, 3, 4, 5 waves. And the orthogonality index is around 4%. And that is pretty good. Even if you use Fourier, you come to that kind of wavelength, you may not have the orthogonality as clean as this. Now, if we add, this is 1 to 2, 2 to 3, 3 to 4. But when you add all the off-diagonal components, that I equal to j, that's more than just this to that. That's 1 to 2, 1 to 3, 1 to 4, 1 to 5, 1 to everything. You add all this off-diagonal thing. All the off-diagonal components may have both positive and negative and all that. You add up to 4%. So this decomposition, I trust it to be good. Yeah. So orthogonality index should always be checked. And check that. The step to check is given here. And in our in the software that we're going to distribute to you, it will have this thing in there. So the orthogonality is not a requirement, but it should be checked all the time. Now, the third one is uniqueness. The uniqueness is EMD with different critical parameter can generate a finite IMF. The result is unique only with respect to the parameters you choose. Yeah. EMD actually can generate infinite many different trials. Yeah. If you change the criteria, you generate a different one. You change another criteria, you generate another one. So then, when it's unique, the unique is to the criteria you choose. The stoppage criteria, yeah, very simple. I used EMD. So you used natural spline. If I change the spline, of course I will get different answers. Yeah. So the EMD will have different answer with respect to different choice of specifics. Yeah. This is understood. You have to have, when you do the problem, you have to have your criteria carefully write it down. So the next time you come back, you can repeat it. If you do not have written down or recorded, then you may not be able to recreate the result you have. Yeah. However, our present is based on cubic spline. So if you use different spline, then you will use different answers. Then you may ask, well, if I keep on getting different results, then how can I trust it? Okay. My suggestion is that you should use ensemble. Yeah. You use one method, you generate one result. I'll try another criteria, I get a different result. How different are these two different results? Are they really different dramatically, or the difference is very, very small? And if its difference is small, then we'll use this difference. We'll get a mean, and we will treat that mean as our answer. And then I will know, but by using different results, what's the sensitivity of the method? Okay, I will discuss this confidence limit in the course. Yeah. So this uniqueness is unique within the the parameters you choose. For example, say I'll use wavelet to analyze the problem. Is wavelet unique? Of course. Wavelet is unique based upon the base you choose. Yeah. If you use different bases, you're going to get different results, of course. Yeah. You should not expect to use hard wavelet to get the same result as, say, Debussy wavelet or Mollad wavelet. They are different bases, just like there are different splines. There are different stoppage criteria. So EMD is a general method. Under this general, EMD should be treated as a general term like wavelet. And in this wavelet, it has all kinds of different things. Yeah. So far, I have used natural cubic spline. Natural cubic spline. Yeah. If you decide that I'm not going to use natural spline, I'm going to start a new program with a different spline. Indeed, there are many people try to implement different splines. Yeah. Then you can compare the answers. Yeah. And the different parameter I submit should not influence, it will influence the minute quantity, but it should not totally disrupt the quality of the answer. Then this quantity, we can use ensemble to find what is nearly true, or the truth. So before I get into other problems, I would teach you a few tricks, very, very simple tricks that that I used before. These tricks that I used before we find the true ensemble EMDs. Yeah, the true these few tricks that I use is that sometimes you just take a problem, you use EMD, you find, gee, the answer is terrible. Yeah. And we did not find that at the beginning. The problem that we treat are very, very simple and benign. Because when I first developed the method, the computer I use is 286. Yeah. So we can only treat extremely simple problem, and for short data length, no more than 1,000 points or something like that. If I put 2,000 points in there, then I have to take a whole day just to process one data. Now, so strict application sometimes may not generate a good result. And using intermittency, you get better. Yeah, but that's not, it's not enough. And sometimes I use curvature, and this is one trick that I used before, is to add low level noise. Yeah. And this eventually led to the true ensemble. That means we add high level noise. We don't add only low level noise. But low level noise, however, sometimes make wonder. Example of low level noise. Here, I have two waves. If I have this wave plus this wave, these two waves propagate together and combine into this wave. And if I want to shift this wave, I'll give you this data. Is it decompose it? can you get back to this two wave? Most likely you cannot. If you use strict EMD, the result is like this. I'll get this component, this component, this component. You get this totally, even this end is filled up, and I have a very large alias. So it's terrible. A lot of people say, well, EMD doesn't work. I agree with them. EMD does not work very well for this case. And especially when you have problem has lots of zeros. Lots of zero present a problem. Obvious problem is where's the maximum? Where's the minimum? Yeah. So you immediately run into problem. Yeah. So in this case, my trick at that time is to add a little bit noise. This noise is 1/1000th of my original data. The amplitude of the noise is 1/1000th. So you add the noise to it. This is data. This is my noise. Okay? I added to it to get this. Can you see the difference? Probably not. Most likely you cannot see the difference. So with this data, then that saved us. Why? Because I have maximum minimum all over the place. And the noise has another nice property is that by adding white noise, when I say noise, I say white noise. Okay? By adding white noise, it has the scale of every length. So you will immediately have that. Have extrema everywhere. Then you go make the shifting. You get only few components. Yeah. And that few components, however, if you compute the orthogonality of these two components, you find the orthogonality of these two components are very poor. And they are almost, excuse me, they are not orthogonal to each other. And not only they are not orthogonal, they are almost the same. So in that case, you know that I'm encounter a problem of one component split in two. Why one component can split in two? When we discuss the ensemble EMD, we'll see that when you add noise, the noise has overlap. The spectrums overlap. We'll discuss that shortly. Okay. So if you add these two together to form the other component, you actually will recover the first component is almost your first. The first component is first EMD is almost your first component. Yeah. You recover the data to a very high degree of fidelity, and when you have 2 + 3, you almost recover the second component. Yeah. So EMD, it's not, if you take EMD and just push a button, try to get the answer, you most likely won't get it. Yeah. Even if we have the ensemble EMD, we'll discuss later, you still will not just get it blindly, so you push a button, the answer presents itself in your computer. Yeah. The EMD at this time, without the rigorous mathematical proof, there's a small elements of art in it. It's not a total science. So you have to look at the data. You have to think. You have to make a judgment. Yeah. And so right now, what do we have is that we have data, we sift. We will have ensemble EMD, we have intermittency, we get IMF. We check the orthogonality index and compute the instantaneous frequency, which we'll talk about, and get the Hilbert spectrum. Yeah. And the Hilbert spectrum, we get a marginal spectrum. This is the whole thing. That here now we are concerned ourselves in this. We talk about the sifted. We talk about some intermittency test. And the next time we're going to talk about the ensemble EMD. Okay? Now, before we talk about ensemble EMD, I want to talk about a little bit about the spline. We are 10 minutes to the end of this class, and we have been interrupted about 10 minutes. So what do you think? Should we start the spline, or we leave the spline to discuss the spline in the totality in the next class? Why don't I stop here, because it's a good place to stop. And I will invite people to ask questions. Yeah. Do you have any questions? Hiroshima? Can you hear me? Well,
yes.
You have any questions? Oh, by the way, I have an announcement to make. This, I think, does not apply to all the other sites, telesites, but apply to this class. Okay. I will encourage you to ask questions. If anybody asks questions, I will definitely add a few points to your final grade. Okay. Anybody asks question in class, then anybody asks question after class, I will take a few points away from your final. The reason is that if you ask a question after class, you benefit yourself, and you take my time away. Yeah. So that's you don't benefit other people. If you ask question in class, you benefit everybody. So I would encourage that. Okay. If you come to me, ask question after class, I would treat you a little bit worse than you not ask questions. Yeah. But however, that doesn't mean that I do not accept questions. You have a very, long-winded questions. You have some really fundamental doubts. You can still come to me. We'll discuss, but not specific questions like what I presented in the class. Yeah. That's encouragement for you to clear your mind before you leave the classroom. Yeah. Any questions? Any questions, Tokyo?
Yeah. I have one question.
Yes.
This is a very small one.
Yeah.
You talked about the uniqueness of the HHT.
Yes.
So I calculate some simple example using the HHT. So in that case, I connect two different two sinusoidal function with different frequency, just connection. So I calculate the Hilbert spectrum. In that case, so I use the different the sampling frequency for the sinusoidal function.
Yes.
So in that case, I got a slightly different Hilbert spectrum. So
yes.
it's I think it is how can I say, maybe so that the connection is continuous, but it is not smooth. So then, okay. So I can get the slightly different Hilbert spectrum. So if I use the different sampling frequency.
Okay.
So such kind of a difference, how can I consider this kind of difference?
Yeah. Your question is not a question of uniqueness. Your question is question on your problem is a problem on sampling rate.
Yes.
For example, we have proved that the Fourier trigonometry function is a bona fide good basis. And if you use a different sampling rate, you get a different spectrum. And that doesn't imply Fourier spectrum or Fourier analysis is not unique. That only implies sampling rate is an issue. Okay? We will discuss that. We'll discuss that. That's not a uniqueness problem. Okay?
Yeah, I see.
You see my...
Okay, I got that. Okay, thank you very much.
Well, that's a good question anyway. All the questions are good.
Thank you very much.
Every question is good. By the way, what's your name?
So, Morikawa.
Morikawa, you make sure you let me know. Write an email to me that you asked a question. I will make a point that you ask a question in the class.
Okay, thank you.
Okay. Any more? You see, any question will actually clarify your thinking. Yeah. He raised his hand even though he chose to sit in the far back. You see, this is the difficulty that you choose your seat so far back. I don't understand. I cannot hear you. Could you come forward? Why you sit so far back? You think I didn't use deodorant? Pangting is fine. This is I did not discriminate Pangting.
My question is, how do you define the
Define what?
The nose?
你用中文问。
我的问题是啊，你不是加一个 nose 吗？对，后面有一个例子是加 nose，why nose？
Noise. Okay. How to define noise? The question is what kind of noise I add? I add white noise. White noise. Its spectrum is white. White noise is there are uniform distributed white noise, Gaussian distributed white noise. There are all kinds of noise. All white noise will work. Okay. So just add noise and then using your maximum to be small. And here the noise I used is uniform white noise. Yeah. The amplitude of the noise to be small. Typically, when you add noise, the noise has the unit value of noise. You multiply that unit value by 1,000, so divide by the 1,000. So your amplitude is very small. Okay? Yes? Pardon?
How to calculate that?
In other words, what you ask is when should I add noise or when I shouldn't add noise. I teach you this trick is when just before we invented the ensemble EMD, which I'll cover immediately next time. At that time, the problem that I encountered is when I have most time is when I have a quiescent region. I mean, that region has no extreme at all, zero, constant. Whenever you have constant, you should consider add a little bit noise just to populate that particular area with extremas. Yeah, because the EMD only identify maximum minimum. If for any location you don't have maximum and minimum, you cannot identify maximum and minimum. This is considered add a little bit. For example, when I process the earthquake data, at that time there's one of the applications that I add noise. The earthquake data, especially earthquake signal, there are different kinds of sensors. One is a seismometer, which is on all the time. Yeah, but when the big earthquake comes, the signal overwhelms the sensitivity, so you get signal clipped. The other one is called the strong force, strong motion. Strong motion, it sits there, it doesn't record, but it has a buffer. When you get it kicked on, then it takes the buffer to what? Data log, it has how many seconds buffering in there? Couple of seconds. 20 seconds data. So when it's kicked on, immediately they start to record 20 minutes before it gets kicked on, and then continuously record until the signal becomes small. So at the beginning, it's quiet, and suddenly a small signal comes, and then a big signal. So when you sift that data, you have a section, it's zero. And where's the maximum? You don't know the maximum. You don't know the minimum. And so that end is start to fluctuate, just like the example that I give. And that really bothered me. So the way that I take care of that is I introduce a little bit noise. And I was able to hold that end down. Yeah. That was the trick that I used. So I thought I will introduce that trick to you, just in case you encounter this problem, you say the EMD doesn't work. It does, provided you add a little bit noise to help you. Noise actually is our friend, not an enemy. Yeah, it helps us a lot. Later you'll find. Yeah. Okay? Yes. Oh, by the way, in your homework or whatever, when you hand it to me, mark on the homework that I have asked a question. Write down your question too, so that I will treat your homework kinder. Yeah. Yes.
My question is, if you actually know what the frequency is, what do you suggest, what kind of EMD should apply?
I introduced a lot of, I may have confused you. I only introduced one EMD. The one EMD is cubic, natural cubic spline using extrema. Only in real case, you want to try curvature, but most of the time you don't. Okay? So you use extrema. Use extrema, use cubic spline. And I will explain why I use cubic spline, natural cubic spline. Because there are different kind of spline, different kind of cubic spline even. Okay? Next time I will discuss I will introduce you to the Libby spline as a justification to answer most people's question why you use cubic spline. Okay, so I use EMD is based on natural cubic spline. Okay, based on extrema. In rare occasion, I use curvature, but I use it sparsely, very rare. Okay, so if you have any frequency, have any problem, please use cubic spline and use the EMD that I presented here. Okay.
Point A, the cubic spline checks you to the extreme.
Yeah.
But curvature you're talking about is
No. It's still extrema. Still extrema.
But how you get I assume you get a curvature
from the data, of course. When I use curvature, I will compute the max. When I use extrema, I only compute the x prime equal to 0, right? I only have these points. When I consider curvature, I will calculate the curvature everywhere. Of course, this is a curvature maximum, curvature extrema. This is another curvature extrema. This is concave upward, concave downward, concave upward. They are all curvature extrema. But then here I have another curvature extrema. This for curvature. If you compute the curvature, you have another extrema here, another extrema here. So then the set of extrema becomes more. Yeah, here this is a curvature extrema too. No, yeah, the curve. This is not. But then when you still connect the envelope. When you get the curvature maximum here, maximum here, maximum here.
Yeah, then you find
connect still maximum, still extrema. But this time the extrema is extrema of curvature rather than extrema of the data. You follow me? So this is all concave downward. This is concave downward. This is concave downward. This is concave upward, concave upward, concave upward. So there are different kind of extrema in their curvature, radius curvature. So you connect all the radius curvature extrema. Yeah. Okay. So
When we talk about spline, usually we take part of data spline to the original data set.
no, not to the original.
But you are taking the curved spline to the extrema to connect extrema, so you can interpolation.
Yeah, I always connected spline with extrema. I never connect spline to the data. Spline is from here, in the original, from here to here to here. If I have curvature, I connect here to here, then to here. Spline is always to extrema. This is the spline curve. This is your data. The spline is applied to here. Say I connect spline here. I did not ignore here. If I use curvature, I would connect this point, and the minimum I will connect to that point. So it will be different. Yeah. So the higher the order you use, the more data point you have to go through. But then you have to be careful of what you got. Yeah. Because in some nonlinear problem, there are waveforms which the hidden scale is caused by intra-wave frequency modulation rather than exactly 2 time scales. Okay? All right.